Welcome to the 10th session of the 2018 Extraordinary Technology Conference. We are very pleased to bring you Tom Valone and Brian Ahern from the Integrity Research Institute. In this presentation, they will inform us about the ongoing experiments with vacuum energy via nanotechnology, particularly the enigmatic device invented by Arthur Manelas, utilizing nanograin strontium ferrite as an oscillating power source to recharge batteries with apparent over-unity for over 20 months. And here now is Tom Valone.
Thank you. I'm glad to be here and privileged to give you this research and information before we introduce our next expert on the subject. The interesting literature search that I did, besides interviewing 3 researchers that have worked with this Manelas device, basically allowed me to narrow down the focus of what we're actually dealing with. To summarize what you're about to hear about, the first part I think you should know is that we're talking about a strontium ferrite product that seems to be like a ferrite magnet. Barium ferrite is often something similar, but this was SR-Fe12O19 in case you need the actual chemical arrangement. The first article I came across, which I thought was interesting, PLOS1 journal article, specifically is entitled Magnetoelectric Response in Multiferroic Strontium Ferrite Ceramics. And magnetoelectric is definitely something that raises my eyebrows because that combines 2 different phenomena that actually are worthy of some response that perhaps might, as it points out in the abstract, relate to a giant magnetocapacitance effect in strontium ferrite. So immediately in the journal articles, I'm already seeing unusual properties of this ferrite that we're about to see and hear about. Secondly, what I came across, and these are only 2 journal articles of many that are dozens that are online. The second one I found was from the International Journal of Research in Engineering and Technology. And specifically what this was entitled, and this is entitled, is Flexible Microwave Absorber based on strontium ferrite rubber composite for X-band applications. And so, once again, this is actually very close to what we're dealing with, a nanoferrite arrangement that has this unusual property of being broadband EM wave absorption material and can absorb microwave energy when incident on the dispersive material. And they claim causes heating in the radar absorbing materials. So it definitely piqued my interest, and of course when I started interviewing the people who actually worked with the Manelas device, which is called the billet, that's put into a battery, but the billet, which may be actually passed around here so you can actually see what we're talking about, is actually not only embedded with some smaller magnets, or at least treated in 5 places with smaller magnets perhaps, but also wrapped with coils in 3 different directions for oscillation purposes. So there are some circuitry frequency absorption that seem to be very important to its transducing of energy. So let me just highlight 2 things that I thought I'd call your attention to as you hear this presentation with 2 different slideshows. Number 1 is related to the Floyd-Sweet invention, which was very similar to this, using barium ferrite, however. And perhaps you could relate it to a solid-state Searle device, which at least 1 or more people have alluded to, mainly because this is only the 2nd device in my life that I've heard about that gets cool when energy is produced. May be interesting. Normally we would expect the opposite, exothermic. This is endothermic. And the other interesting phenomena, which was very, I would say, a one-time occurrence, and perhaps Brian will allude to it and describe it, was they left the batteries with the billets in them in the garage for a time, several hours, and when they came back, apparently every battery had not, the word was exploded, but it meant every battery had expanded considerably. Now, of course, they weren't disabled completely, but they apparently had a lot of energy discharge. So these are one of, or two of many different anomalies that can actually make you more interested in what we're about to talk about. Besides the fact that it can run an electric car, seems to increase in voltage, and so forth. So without further ado, let me just talk to you about the researcher you're about to hear from. Specifically, Dr. Brian Ahern has a PhD in engineering from MIT, did independent laboratory testing of the device, worked with Arthur Manelas before his passing, and his first slideshow will be on energy localization, which you see here. And specifically, he did his doctorate thesis on a semiconductor crystal growth, which seems to be an analogous field of interest, but he also worked for the DoD, USAF, Quantum Catalytics, and Rome Laboratories. So he's worked on contracts with the Energy and Power Research Institute, also called EPRI, and he's received awards in technology transfer, national technology, a second prize from the Department of Energy competition on clean energy, and his work began on the Manelas Device in 2011 and has several articles dealing with this. And then afterwards, after he finishes this, you'll see the actual slideshow on the Manelas Device as well. So talking first on the topic of energy localization, please welcome Brian Ahern.
Good evening. I'd like to thank Tom Valone and the Integrity Research Institute for this presentation. And I have to make an apology at the beginning. One is for my Boston accent. It's tough to listen to for a lot of people, but that's what I've got. And next, I'd also like to apologize in advance because I'm going to come off as arrogant as all get out. I'm going to be bombastic. But that's the story I have to tell you. I was at the confluence of three major areas of research over the last 30 years: superconductivity, nanotechnology, and energy research. I was thrust into it, and I'd like to explain some of that to you. Back in 1935, a Nobel laureate named Landau met up with Edward Teller in Copenhagen and said, "Edward, you have more money than God. I want you to look at this perovskite mineral. It has unusual vibrational properties." So Teller took it home, gave it to his graduate student, Hermann Jahn, and 2 years later they wrote something called the Jahn-Teller thesis. It wasn't a very big deal, but it led to some very big deals years later. In 1987, there was great news around the scientific community where high-temperature superconductors were discovered. And what we're looking at down here is a puck made of black powder that had been pressed together, then ground again, pressed together, ground again, pressed together. And eventually, it floated a magnet. And that was, at the time, enough to say that this is a superconductor. It took me about 2 weeks to do that in April of '87, and another week to do it a third time. And I said, okay, that's enough. Why would I want to do it anymore? But my lab director said, I was at an Air Force lab, and we were the lead in trying to understand this for the Department of Defense. So the Navy and the Army took second chair, and they asked the Air Force to study the project. And my lab director handed it over to me, and I said, geez, why me? I always had a kind of an attitude like, if I keep my mouth shut, nobody will know I'm incompetent. But if I open it, that'll leave no doubt. So I was very circumspect. But he said, you have to take the lead because I did a thesis on superconductivity in 1975. And just coincidentally, it was the material for the cold fusion that happened in 1989. So I did it 14 years before Pons and Fleischmann. So my job was to find anybody who knew how these new superconductors worked. And I was clever. My laboratory had a big budget for education, but none of the PhDs really wanted any more schooling. So I asked, can I have a seminar series? I'll invite people in to speak and pay them very well. Well, I paid them stupidly well. I paid $5,000 for a 1-hour lecture. The word got out soon, and a lot of people want to make that talk. And every one of them sounded great from A to Z. They were different, but they sounded great. But I was giving up hope until I was walking across Harvard Square in 1988, and I bumped into an old professor of mine from MIT named Keith Johnson. I asked him if he had solved the problem. Like all theoreticians, they say, oh yes, that's behind me now. I solved that years ago. So I went to get his paper, and in 1983, he did indeed write a paper on high-temperature superconductors. He presented it in Zurich at the International Conference on Superconductivity, and he held up the same type of perovskite that Landau and Edwin Teller used in 35. He said, if you want high-temperature superconductors, look in the perovskite system. Well, the head of the conference was named Mueller, Alex Mueller, and he gave it to his assistant Bednorz, and 4 years later, they won the Nobel Prize, still not understanding a word of what happened. So I knew then and there in 88 that we were 30 years ahead of our time. I said it in 88, we're 30 years ahead of our time. And to this day, 2018, 30 years later, there isn't one person in this room who knows anybody who knows how the superconductors work. There aren't 5 people in the world. It's not a big deal. It would take 3 or 4 hours to explain it. Then you'd be at the same level, not 30 years behind. And that was also true of another bit of technology, but I wanted to say, I'm going to talk about 3 powders. The nanopowders that made the superconductor, the nanopowders that made the Manelas device, and I think that's being handed around. Corey, did you find? Okay. Somewhere in this room there's a black billet that was made of strontium titanate, but it was made of nanopowders. And then there was a third sample that I worked on when I was talking about Arata, the scientist from Japan, and I want to go forward with that. Johnson would take a central atom, call it iron, and surround it by its nearest neighbors. You can put 6 spheres next to any sphere, and then you can put 8 spheres in the second position. So 8 plus 1 plus 12 is, what is that? 21. Each one of them has 26 electrons. That comes out to be 546 electrons. And if you can account for where they go, you can represent the properties of iron with just 21 atoms. And that's what Johnson did. And he could show the properties of any material system. But it had to be, you had to account for not only all those 546 electrons, but you had to account for what kind of orbitals they went into. And they can go into bonding orbitals and anti-bonding orbitals. And every engineer in this room never heard of an anti-bonding orbital. You don't deal with it. But Johnson showed that if you didn't, you can't account for any of the physical properties. You can never describe superconductivity. And you can never describe ferromagnetism. So there are things that are not understood. Superconductivity. You probably thought ferromagnetism in materials was understood. It is not. Nobody claims that it is. I'm having trouble reading that, but Oh, excuse me.
Yeah, Kevin, all these screens around here, they're all the same. That way, everybody gets your good side, the front side.
Thank you. Well, we talked about superconductors with Johnson. Oh, boy. When I was studying for materials with Johnson and superconductivity, we ran across a paper called FPU, Fermi, Pasta, and Ulam, where they did a simulation on a computer in 1953 at Los Alamos. And it was one of the first simulations ever done. And what they did was they took an array of masses connected by springs and then gave them a little energy input, a transverse mode or a longitudinal mode, let it run for 10,000 cycles, and they found that every one of those masses in blue got the same amount of energy. That's the equipartition of energy, and that's good that that happened. But then Ulam said, instead of F equals minus kx, let's add another term. Let's turn this from a linear problem into a nonlinear problem. And what happens? Well, when you add the nonlinear effect in, you can see that you get very large amplitude oscillation modes over a localized area. But if you look at the left and right, you get very small modes. So they are vibrationally cold. And thermal energy will come in through those cold regions and up pump to the high energy modes. They saw that this happens when you have two conditions: a countable number of things, masses, and nonlinear coupling. Well, a countable number means just not too many. If you have too many masses, you never get any feedback. Now, it's hard to see, but you've got a tray of BBs, and they're vibrating like an old little football game table, and the BBs vibrate with an amplitude of about 1 BB. But if you put a nonlinear arrangement in, that is, put a little static charge, then they have a nonlinear coupling, and you can see you get enormous vibrational modes. If those were atoms, those would be breaking bonds and forming new bonds, and so it makes it catalytically active. And this is how nature carries out all its energetic processes through enzymes, which have their size, a countable number of atoms. And we found, oh boy, I don't know where that came from. A countable number of atoms, and we had nonlinear coupling. When you have both of those two things, you can get energy localization by having the vibrational modes greatly increase locally at the expense of cold ones around it. And this provides kind of a shortcut around the second law of thermodynamics. Nature can assemble ordered structures without a temperature gradient by energy localization. It has to do it between 3 and 12 nanometers. Above that, you don't get the localization. Below that, you don't. So this, I think, is still the most profound discovery in nanotechnology to date. And it accounts for everything that nature does, the fireflies, high efficiency, and so on. So there's just a picture. And this work was done, the simulation was done at Los Alamos. And this verification with a real system was done at the University of New Mexico. This was the cover story in Nature in August 1996. And it was called Oscillons Observed. The reason people can't deal with it is they're not aware of that energy localization having two conditions: a countable number and nonlinear coupling. Now, how do you get that out of a small number of materials? Well, when you get near the surface of any material, the bonds become shallow and distended. So for the first 3 or 4 atoms in a material, they are nonlinearly coupled, as the bonding is not linear. So when you get to a nanoparticle, a lot of the atoms are near the surface. So if you get down under 12 nanometers, you get enough nonlinear coupling to instigate this energy localization process. So every enzymatic process uses it, and we used it to make artificial light emitters. And in 2001, we had the world's most efficient light source when we processed at 10 nanometers. A company in Lexington, Mass. Recently iterated to that size regime, but they were just bought out by the Chinese last month. There's a picture. That was done in 1997, and that was a report for an SBIR program we had going. This is just another diagram for light emission. So what are the advantages from going from 100 nanometers to 10 nanometers? It's not just making things smaller. I'm going to show you in a minute a professor from Japan named Yoshiaki Arata. He made a presentation in Washington, D.C., saying that he got energy out of nanopowders by adding hydrogen, and they would heat up, form the hydride, and cool down, but they would never cool back to room temperature. But the very next speaker at that conference in 2008 got up and said, "We did what Professor Arata did. We didn't see anything." So when I asked how things went at the conference, they said there was nothing new. This little old guy in a wheelchair said he had an effect, and this handsome, virile, younger guy said he didn't see anything, so Arata was ignored. But I knew about the magic because Arata said he processed at 10 nanometers, and the other fellow processed at 100. So by a series of emails, I convinced him, you've got to go from 100 to 10. I'll give it to you if you want. And sure enough, it worked the first time. That was in 2009. So there's something magic about the size regime from 3 to 12 nanometers that is inescapable, and I think it's behind a lot of the things we're talking about. So that's energy localization. Light emitters, solar cells, photosynthesis, but mostly enzyme functionality. We have tens of thousands of enzymes, and they all work on energy localization. And now I want to talk about energy production and nanomagnetism. I'll skip that one. There's Yoshiaki Arata. I never heard of him. You never heard of him. But he was the most decorated scientist in the history of Japan. He's wearing the Emperor's Lotus Medal. He died in March at the age of 94. But he was processing materials at 10 nanometers. And after I corrected the other fellow named Takahashi, I went to the Electric Power Research Institute and I said, I'd like you to pay for materials. I'll do the work with no salary or overhead, and I will verify what Arata did. And I did that, and that's in the published report for EPRI from 2012. So energy localization was explained to Takahashi in February 2009, and he was successful by March 2009. He reported it at the 20th anniversary of the cold fusion effect. This is just showing some transmission electron microscopy, showing that you've got indeed, the legend down there, that's 10 nanometers, and that's what the particle size were. And when you had those, you could see excess energy. So now I'm switching away from energy localization, and I think this is just, ferromagnetism is a cooperative process, but we don't understand how ferromagnetism arises from the topology of the molecular orbital bonds. That has never been solved. But we know that energy localization amplifies the process. Again, we've already seen that. With regard to nanomagnetism, ferromagnets have a magnetic property, but they also have a conduction property. And strontium ferrite is a very strong magnetic field. 2.2 kilogauss, but it has a very, very high electrical resistivity. So if you try and put an electromagnetic wave through it, you get the magnetic system moving, but you can't induce eddy currents because it's too resistive. So if you wanted to have something that was over unity, the first thing you want to do is have it very good under unity. And that's what this material is. It's great. It's got a strong field, has high resistivity. And now if we can also address the grain size to be down in that 3 to 12 nanometers, then you've got all the things you want for amplification. We already talked about energy localization, the nonlinear feedback effect. Oh, it was done by Fermi, Pasta, and Ulam right down the road at Los Alamos National Lab. My son is here today. He's a scientist at Los Alamos Lab. That was one of the reasons I wanted to come out here, to see the place where Fermi, Pasta, and Ulam did their work. Now, Ulam was a mathematician. He's the one who suggested they do the simulation by adding the nonlinear term. He did that in 1953, and in 1954 the Russians detonated a 60 megaton nuclear warhead, and everything, and I mean everything at Los Alamos, became classified. And that experiment never saw light of day for 30 years. That simulation was, when it was done, there was one computer west of the Mississippi. But in '88, everybody had an IBM desktop. And it was easy to do and easy to repeat in 1, 2, and 3 dimensions. But it was only done by mathematical physicists who know nothing about chemical bonds, whether they're linear or nonlinear. I had come from the superconduction issue where you had to have nonlinear bonds. That's what the perovskite minerals do. Most materials, solids, vibrate like this. Small amplitude, high frequency. Perovskites, which are those high temperature superconductors, they do this. 100 times smaller, lower in frequency, and 10 times larger in amplitude. Before the perovskites came along, it was thought by Ulam and Fermi and others, and by Born and Oppenheimer, that you could decouple the motion of an electron from the nuclear core. Because the electrons are so light and the nuclei are heavy, we can treat them independently. And that's a great assumption to make. That's the Born-Oppenheimer approximation. But Edwin Teller and Hermann Jahn found that under circumstances where you have those long, shallow potential wells, you do get coupling between the electrons in the vibrational modes. If you get coupling between the electrons to the vibrational modes,